Hello everyone, my name is Koichiro Saito. I'm a sophomore at Purdue, and today I will be going over some Exam 1, Exam 2, and final exam questions for MA 262. I will do two of each. Okay, first question. Question 3. Let y of x satisfy y prime of x plus 2x over 1 plus x squared times y is equal to negative 2x y squared, with the initial condition y of 0 equals 1. Then y of 1 is equal to blank. You have a bunch of options. Okay, at first glance, this kind of looks like a first order linear differential equation that follows the form y prime of x plus qx y is equal to p of x. And we know how to solve these. We multiply through by an integrating factor, and pretty easy to solve. However, we have an additional y squared term, which makes this a little bit more annoying. Because now, instead of a first order linear differential equation, this is a Bernoulli's equation. We know this is a Bernoulli's equation because there is an additional term here. And since here, the additional term is y squared, we know that n is equal to 2. In Bernoulli's equations, we know that n cannot equal 0 or 1. Okay, this is Bernoulli's equation. We know n can't equal 0, because then that would just be a first order linear differential equation. And we know that n can't equal 1, because then that would be a separable equation. And those both have different kind of simpler ways to solve them. But since this is a little bit more complicated, we have to use a substitution to simplify it. And the substitution we like to use is v equals y to the 1 minus n. So let us use this substitution. Okay, v equals 1, y to the 1 minus n. And we said n is 2 in our case, because y is being raised to the second power. So we know it's 2. Okay, so v is 1 to the negative 1. Okay, in Bernoulli's equations, we're trying to rewrite this original equation in terms of v and x. So we want to replace all the y's with v's. But there is a dy dx term, and we want to replace that with a dv dx. So we have to think of a way that we can rewrite dv dx in terms of dy dx. And I think a good way to do that is to differentiate the substitution that we just made. So let's do that. dv dx is equal to, let's differentiate this. We bring the negative 1 down. Negative y to the, and now we subtract 1 from this. So we get y to the negative 2 dy over dx. Okay, we can multiply both of these by negative y squared to isolate the dy dx. And we get negative y squared dv dx is equal to dy dx. Okay, now let us plug this into this equation. Let's do that. So what we get is negative y squared dv over dx plus 2x over 1 plus x squared y is equal to negative 2x y squared. Okay. Let's try to isolate this dv dx term. Okay, so let's divide through by negative 1 over, or divide through by negative y squared. Okay, so when we do that, we isolate the dv dx term like we wanted. Here, we have 2x over 1 plus 1 becomes negative because of the negative sign. 2x over 1 plus x squared, and y divided by y squared is 1 over y, equals negative 2xy squared divided by negative y squared is just 2 of x, or 2x. Okay, we still have a 1 over y term here, and we want to write this only in terms of v and x. So what do? Well, earlier we said that v is equal to y to the negative 1. So let's just rewrite this as v, right? Because here it just says v is equal to 1 over y. and this is 1 over y. So we can just rewrite this in terms of v. Okay, so now we have dv dx minus 2x over 1 plus x squared times v is equal to 2x. Okay, now this is looking like a real first-order linear differential equation, which is what we talked about earlier, right? Which follows the form y prime of x plus q of x y equal to p of x. And we know how to solve these. We can use an integrating factor and multiply the entire equation. And we can find that integrating factor using this. I is equal to e raised to the integral of q of x. Okay, so let's do that. But what is q of x in our equation? We know that q of x is just this. Yes, because we have it in the standard form of a first-order linear differential equation. Okay, so let's find our integrating factor. I is equal to e to the q of x dx. And q of x equal to negative 2x over 1 plus x squared. Okay. E to the negative 2x over 1 plus x squared dx. Since negative 1 is a constant multiplier, we can just pull it out of the integral. Okay, now let's use a u substitution. Let u equal 1 plus x squared, and that's, if we differentiate both, du is equal to 2x dx. Okay, so that means we can rewrite this integral as negative du over u, which is just e to the negative natural log of u. But u, like we said earlier, is just 1 plus x squared. Negative natural log of 1 plus x squared. Okay, we can do a little bit more here. We see here that there's a negative sign in front of the natural log. And we know a very common natural log rule is that if you have a constant multiplier in front of a natural log, you can rewrite that as an exponent. And this may not look like a constant multiplier because it's just a negative, but we can just pretend that it's just being multiplied by negative 1. So we can bring that negative 1 and bring it up here. So it's just negative 1. Okay. We also know that e to the natural log of x is just equal to x. So we can just rewrite this as I is equal to y 1 plus x squared to the negative 1. Okay, very good. So we know that I is equal to 1 over 1 plus x squared. Because negative 1 just means, you're putting it on the denominator. Okay, cool. Now let's multiply this entire thing by I. Because that's how you solve first-order linear differential equations. You find the integrating factor and then you multiply through. So let's do that. Our integrating factor is 1 over 1 plus x squared. I'm going to move that a little bit over. Okay. dv dx times 1 over 1 plus x squared. That's just going to be 1 over 1 plus x squared minus 2x. Since when we multiply a 1 plus x squared here, and we already have a 1 plus x squared here, this just becomes 1 plus x squared over 2 times v is equal to 2x over 1 plus x squared. Okay, when we do an integrating factor problem, after we multiply by the integrating factor, what we're looking for is the result of a product rule. Okay, what I mean by that is, let's remember the general form of the product rule, which is you know that to differentiate a product rule, one of the terms remains unchanged in the first term, and one of them is differentiated. And in the second term, one of the terms is differentiated and another is kept the same. Now let's try to apply that to what we found here. Okay, we can see that dv dx was differentiated on this side, but was left alone on this side, and it's just v. We'll see that 1 over 1 plus x squared was left alone here, but over here, it was differentiated, right? Okay, I hope that is clear. Okay, let me just erase this. Okay, so let's look for the product rule. I think the product rule is v over 1 over 1 plus x squared d over dx equals 2x over 1 plus x squared. Let's test what we said earlier. V was differentiated here, but was left alone here. 1 over 1 plus x squared was differentiated here. Or no, 1 over 1 plus x squared was left alone here, but differentiated here. Okay, very good. Now let's take the integral of both sides. On the left-hand side, these two just kind of cancel out. And now you have v equals 1 over 1 plus x squared equals, on the right-hand side, we can use a u substitution, let u equal 1 plus x squared, du equals 2x dx. So this is just du over u, which is just natural log of u plus u. So we know that this is natural log of u, which is 1 plus x squared plus c. Okay. Let's rewrite this entire equation in terms of y again, now that we have solved through. Okay, I will do 2 steps at once to rewrite in terms of y. First step is I will rewrite v using our substitution that we found earlier, which is v equals y to the negative 1. Let's do that. Let's rewrite in terms of v equals y to the negative 1. Another thing that I will do is I will multiply both sides by 1 plus x squared. So let's do that. And we'll do it up here. So actually, let's just bring this all up. Okay. When we multiply 1 plus x squared through, we get v, but we're going to rewrite v as y to the negative 1. So we get y to the negative 1 equals natural log of 1 plus x squared plus c times 1 plus x squared. Let's just get rid of this y to the negative 1, so we can raise everything to the negative 1, and then we would get y is equal to 1 over natural log of 1 plus x squared plus c times 1 plus x squared. Because remember, when we raise something to the negative 1 here, using our exponent rules, we know it just kind of cancels out and becomes y to the 1. But here, it just flips everything. Okay, now that we have this particular solution that still has a constant of integration in it, we can use our substitution to find, now that we have a general solution, we can use the initial condition to find the particular solution. Sorry about that. Okay, our initial condition was y of 0 equals 1. Okay, so that means when x equals 0, y has to equal 1. So 1 equals 1 over natural log of 1 plus 0 squared plus c equals 1 plus 0 squared. Okay. Natural log of 1, we know, is 0. This is also 0, because 0 squared is 0. Surprising. So y1 equals 1 over c times 1. So we know that c is equal to 1. Okay, now we have found our general solution. Y is equal to 1 over natural log of 1 plus x squared plus c, but c here is 1, plus 1 times 1 plus x squared. Now, what they're asking you to find is they're asking you to find what y of 1 is equal to. So let's find y of 1. Y of 1 is equal to 1 over natural log of 1 plus 1 squared. I don't know what I just did. Y plus 1 squared plus 1 times 1 plus 1 squared. So we know that it is 1 over natural log of 2 plus 1 times 2. So y of 1 is equal to 1 over 2 natural log 2 plus 2. Let's see if that's one of the answers. And it is. It is answer choice number 1. Quick recap. We recognized it was Bernoulli's equations because there was a y to the n term. Then we used the substitution v equals y to the 1 minus n. We differentiated this to find dv dx in terms of dy dx. We rewrote this original equation in terms of v and x. Once we did that, we recognized this was a first order linear differential equation that can be solved using an integrating factor. Then we found the integrating factor by doing I is equal to e raised to the integral of q of x. And we know that q of x is negative 2x over 1 plus x squared. We found the integrating factor to be I is equal to 1 over 1 plus x squared. Then we multiplied the first order linear differential equation by I, and we got this. Then we used our knowledge of the product rule to rewrite it as v over 1 plus x, 1 over 1 plus x squared d over dx. Then we integrated both sides. Then we got this, v times 1 over 1 plus x squared equals natural log of 1 plus x squared plus c. Then we rewrote it in terms of y. Then we used our initial condition to find our particular solution and the constant of integration. And once we did that, we plugged in the value that was asked for, and then we got our final answer.